Hello and welcome back to CEN 202, Mechanics of Materials. In this unit, we're going to be looking at axial loads. Axial loads are any loads applied to a member along their axis. And if we take a look here on the left, we can see an example of an axial load. Here we have a column on a concrete base. We have applied load, dimensions, etc. And one of the things we want to know is what happens when this load is applied. We've already talked a little bit about strength. Clearly, we want to make sure that the column and the concrete base are strong enough. But once we've determined that, we also want to look at deformation. Also, if there's any unusual effects. For example, things like temperature, stress concentrations, concentrated loads. Those are all things that we need to take into consideration when we're talking about the behavior of a structure under an axial load. Now, these go along with our Hitler text, chapter 4. As always, I recommend you read through it or review it before you go through this presentation, but hopefully these two things will help to support each other. The last two topics we're going to cover in this unit are St. Venant's principle and the associated stress concentrations. So far, when we've looked at loads, we've assumed that the stress is uniformly distributed on the plane. And the fact is we've always used an average stress. And it turns out that in many situations, this distribution is not actually uniform. If you have unusual loading geometry, if you are relatively close to where the load is applied, if you have sudden changes in the geometry of the material, all of these are going to have an effect on how the load is distributed. So let's take a look at that and let's answer the question, how does a concentrated load affect the stress and strains near that load? And the easiest way to represent that is with a compressive load. So here is an example of a situation where we can easily see changes in the distribution of strain, which will give us information about the distribution of stress. So in this case here, we've made a compressive specimen out of a rubber material. Rubber material is selected because it's very elastic and we can significantly deform it without failure. So we've put a grid of regular spaced lines horizontally and vertically on the side of this bar, essentially a net of these lines. In this case here, we're only showing the top half, but it would be mirrored, so the bottom half would essentially look the same way with just a reversed orientation. So we start out with a square structure that we see here. Now, at this point, we're going to put a point load, you can see it right here, located right on the top, and it's applied right here at this point. This is the compressive load, is squeezing the material. And you can clearly see that the elements close to where this load is applied are going to deform at a much higher rate than the elements away from it. The fact is, when you go down far away from where the load is applied, you see that the elements remain essentially rectangular as compared to what's going on at the top, where the elements are deforming and changing shape, clearly getting smaller, narrower, etc. Now, if you look at that in terms of strain, that deformation is directly related to strain. So we can easily say that the strain near the point of application where the load is applied is going to be significantly higher than the strain further away. You can see that right from the diagram. Keep in mind, Hooke's law tells us that stress and strain are connected, and as a result, we can see that if there's a higher level of strain, there must be a higher level of stress. So at the point of application, the stress is significantly higher than away from that point of application. But you could also see that as you get further away, the stress becomes more evenly distributed. Right? As we get to the middle of this beam, shown at the bottom here, the stress looks essentially uniform, where all of the elements are remaining rectangular, all of them are deforming at the same rate. Now, the theory of elasticity shows us that, and essentially what the theory of elasticity does is it looks at Hooke's law and says if you have this much strain, that means you're going to have this much stress, and as a result, we can see what the stress distribution looks like, right? This is shown over here. We have our undeformed beam, right, with a load applied. As we start to look back into the beam, right, we're going to see that the distribution is going to change. So if we were to take a section at b over 4, b being the width of the member, we can see that the distribution of stress is going to be very high with a maximum load here right at the middle, more than 2.5 times the average stress. If we take a look at the load distribution further in, we can see that this stress distribution has dropped off. We still have a peak right here, but it's now it's under 1.5 times the average stress. And if we go eventually to look at the stress distribution at B, again the width of this beam, into it, we see that the distribution is remarkably flat, with the maximum distribution only a little over 1 times the average. If we were to go further in, we'd see that this distribution would flatten out even more. So we can see that the stress smooths out to a nearly uniform distribution at about B distance, right? And B is just a variable. It's the width of it. If you were looking at a cylindrical member, then you could use the diameter. So it works as either the width or the diameter. And what we note is that once we're 1/5 of the member away from that point of application, we have nearly uniform distribution. In fact, nearly uniform in that it varies by only 2.7%, right? So that's pretty close, where we just have a very small change in the distribution and the stress level near the middle. And in fact, you can easily approximate the stress as P over A, and you'll be pretty darn close. It turns out that this original concept was first noticed by a French engineer and mathematician named Bar de Saint-Venant, and pardon my French if I've mispronounced that. He observed that when we look at loads, we see that there's going to be a high localized stress where they're applied, but as you get further away, the load is going to drop off and we're going to have a more uniform distribution. He specifically noticed that when the distance is equal to the width or depth of the member, that this localized effect disappears. And we can use the simple formula for stress that it's equal to just the load divided by the area. And this is referred to as Saint-Venant's principle. While we've shown that this works on a concentrated compressive load, we can actually show that this works out on a wide variety of members and loads as well. This is a relatively simple relationship, and essentially it shows us that these peak loads, where we have a concentrated load, can lead to high levels of stress and deformation. But this is important because keep in mind this is a real stress. So for example, in that first one, we saw that the stress was over 2 times what we would predict by just using an average load. So we need a method for determining what these stress concentrations cause and how these distributions can be determined. As we know from the previous unit, an axial load is going to lead to stress inside a material. Stress is that internal resistance to deformation. In terms of that, we're going to see that there's a relationship between the load and deformation. Deformation, we use the symbol delta. Right? We can see it right here. This is the Greek lowercase delta, or we sometimes use the Greek uppercase delta, so delta L, or change in length. In terms of the deformation, we're going to have elongation when something's in tension. If you pull on something, it's going to get longer. On the other hand, we're going to have foreshortening if it's in compression. If you press on something, it's going to get shorter. Much like stress, we want to make sure that this particular material property is size independent. If you think about what we did with load, we divided out the cross-sectional area. So instead of having a load measurement, we looked at load per square inch. Essentially, we're going to do the same thing with strain. So what we find is that the deformation is directly related to the original length. A longer specimen will stretch more than a shorter specimen. So we want to remove the effect of length. And so how we do that is we use a quantity known as strain. Strain is represented by the Greek letter epsilon. You see right down here, it's like a script E. And essentially, it's the deformation divided by the length. In terms of units, deformation is going to be in inches or millimeters. Length is going to be in inches or millimeters. So if you divide those out, it turns out it's going to be unitless. So it's essentially is just a ratio. Now keep in mind, oftentimes when we talk about strain, we do say that it's in units of inch per inch or millimeters per millimeter so that we know we're talking about two lengths. But it is just a ratio. And the fact is the amount of strain in inch per inch would be exactly the same as the amount of strain in millimeters per millimeter. So for our terminology, if we have an axial load, we describe the stress on the specimen as an axial stress, and we also describe the strain as an axial strain. These are all aligned with each other. So the load is along the axis, the stress would be along the axis, and the strain would be along the axis. Interestingly enough, though, when you have an axial strain, it turns out that you have a smaller strain in the opposite or lateral direction, perpendicular to the load. And you can see that, for example, when you pull on a rubber band. When you pull on a rubber band, you put it in tension, and that axial strain is going to increase its length. But if you were to look at the cross-section, it turns out that the cross-section actually gets smaller. So the cross-section is actually in the opposite direction, and it will decrease in width. And while that clearly happens in a rubber band, it actually happens in all materials. The fact is, the volume of the material you have available has got to remain relatively the same. So when you pull on something and you make it longer, the material has to come from somewhere, so it has to become narrower. Similarly, if you push on something and it's get shorter, the material has to go somewhere, so it actually gets wider. In terms of our sign convention, we call a positive strain tension. Right? So pulling on something in tension leads to a positive strain. When something's in compression, it's called a negative strain. And if you think about it, the change in length, it would be a positive change in length in tension, and it would be a negative change in length in compression. So now let's look at the equations that govern the behavior of axially loaded members. If you recall, Hooke's law states that stress is proportional to strain, and the constant of proportionality is the modulus elasticity. In equation form, that stress, using the symbol sigma, is equal to E, which is our modulus of elasticity, times epsilon, which is our symbol for strain. Keep in mind, both stress and strain have their individual equations. So stress is equal to force divided by area. You may see this written as F at times, or P means the same thing. It's your force divided by area. And as a result, we can then use our Hooke's law to show that this is going to be equal to the modulus times strain, but strain is defined as the deformation divided by the original length. So if we were to define just the deformation, we could manipulate this equation around to show that deformation is equal to force times length divided by area times modulus. If you think about it, your deformation will be increased by an increased load, will be increased by an increased length, will be decreased by an increased area, so a bigger specimen will deform less, and will decrease by an increased modulus of elasticity, so a stiffer material would deform less. This is also going to be written as just stress is equal to length divided by modulus. So there's a number of different ways we can manipulate these various equations to get these different relationships.